Hey everyone, welcome back, and today let's solve Leetcode problem 2583, kth largest sum in a binary tree, the daily Leetcode challenge problem. So we're given the root of a binary tree in a positive integer k. The level sum in the tree is the sum of the values of the nodes that are on the same level. And we have to return the kth largest level sum in the tree, which doesn't necessarily have to be distinct. And if there are fewer than k levels present in the tree, we need to return -1. And note that two nodes are considered to be on the same level if they have the same distance from the root node. So in example 1, they also give us an image to better visualize how this tree would look like, right? And our k value is going to be 2, indicating that we have to return the second largest level sum of all the different nodes that are the same distance from the root in the binary tree. And in this case, that would be 13, right? Because the level sums are going to be the following. Level 1 is just the root node, that's 5. Level 2 is the nodes to the left and right of it, which are 8 plus 9, which is 17. Level 3 is 2 plus 1 plus 3 plus 7, all the nodes to the left and right of these two nodes, which is 2 plus 1 plus 3 plus 7, which is going to give us 13. And level 4 is the nodes to the right and left of these, which is just 4 and 6, which is going to be 10. And the second largest level sum of all of those level sums is going to be 13. And the reason why we take the second largest level sum is because k is 2, and theoretically we could call it the second largest level sum. It doesn't really matter, but it's just second, right? So in example 2, we have the input root to be 1, 2, null 3, and k to be 1, and we'd output 3 because the largest level sum is obviously just the maximum level sum, which in this case is 3, the highest node value in this binary tree. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Alright, so the way the algorithm is going to be structured, we're going to use a BFS, or breadth for search algorithm, because we need to traverse the binary tree level by level, and this ensures that we actually do get the sum of all the node values at each level. And we'll also be using a heap data structure, also known as a min heap in Python, to track the top k largest sums. And a min heap helps us efficiently maintain only the largest sums while discarding all these smaller ones. And we'll also finally be using a queue for our BFS algorithm to keep track of the nodes for each level as we actually traverse the tree in that BFS order. So with that out of the way, let's just go ahead and dive straight into the code here. Theoretically, I don't need to do this. It's optional in these Leetcode editors, right, and IDEs, but I'm just going to do this for best practice. I'm going to, from the collections module in Python, I want to simply import the DQ dependency, or package, if you will. I think that's how you spell DQ. I always struggle with that spelling because of the weird U and E, but I think that's how you spell it. And I'm also going to just import the heapq module after I do that, after I actually import that package from the collections library. All right. So once I do that, now I can actually get into my code. So usually for graph problems, such as this, I typically have a base case just to cover any weird edge cases and inputs where they aren't actually valid. So in this case, the way we're going to structure that base case is, if not root, I simply automatically want to return -1, right? Where again, this checks if the tree is empty, right? If the root is actually none, we want to immediately return -1 because obviously there's no levels to, well, accumulate sums for, right? So after we do that, we can initialize our two data structures, the queue and the min heap. So the min heap is going to be initialized to an empty array, or list, if you will, in Python. And our queue is going, I think that's how you spell it, queue. And that's going to be initialized to an empty double-ended queue, or DQ, with the root value in it at first. The root value, okay? Where again, it's going to be a min heap because obviously that's going to allow us to remove efficiently the smallest sum once the heap actually grows behind the size k. And the queue is going to be initialized with the root node to actually, accurately begin that BFS traversal, right? So now we're going to begin that BFS traversal. So while the queue is still valid, so while queue is not empty, we can do this in Python by simply saying while queue, right? While there actually still are nodes left to still process in the queue, right? We'll have our current level sum to be initialized to 0 because obviously we haven't actually traversed through the nodes in the current level just yet. All right. So the level sum is going to be initialized to 0, and now we'll say for blank in the range of the length of Q. Again, I'm just using this placeholder for my operator because I'm not actually working with this iterator. You can use it for you can name it whatever you want. You can say for I or J. It doesn't really matter. I'm just gonna say for underscore because we're not actually using that iterator to operate with anything using that iterator, right? Where again, this level sum is going to accumulate the sum of all the node values at the current level in this binary tree. And this for loop right here on line 17 simply processes all of those nodes at that current level in the range or the length of the queue, right? Where the length of a queue is going to give us the number of nodes in that current level, right? Where again, that's why it's not really important, or we don't have to really work with this iterator. I'm just going to name it whatever I'd like as a placeholder or a filler variable to iterate through the range of the length or the number of nodes at that current level with the queue. Okay, once I do that, I want my current node to be equal to q.pop_left. And I'm going to have my level sum to be incremented by that node value. So I'm going to say in Python, node.val. Okay? So we basically have to first remove the first node from the queue for actual processing on line 18, where we say node equals q.pop_left, and we have to increment or add the value of the current node at that level to the current level sum, right? So now we have to check for that node's children. So if node.left actually exists, if it's non-null, we also want to add to our queue, or q.append node.left, right? The node to the left of that current node in the current level of the binary search tree. And also, if node.right, we also want to add to our q.append, the node.right, or the node to the right, okay? Where if the current node has a left or right child, we have to add those nodes to the queue, and this ensures that all of those nodes at that next level are actually processed in the next iteration of the while loop, right? When we actually move on to the next iteration of the while loop. All right, so outside of this for loop right here, now I want to set heap q dot heap push onto my min heap the current level sum. Sorry, this should be within the while loop. Right? So again, we simply have to add this current level sum for this current iteration of the current level in the binary tree to the min heap, okay? Which again is going to keep track of all the different current level sums and actually efficiently return that kth largest sum of all the different level sums in the binary tree while this while loop is still running. So while we still have elements or nodes to process in our double-ended queue, okay? So now we have to check if the length of the minimum heap, which stores the values of all of these different level sums, if that's actually exceeding the k value, which is again the input, right? Remember that? We want to pop from our queue. So keep q.heap pop, right? So if the size, again, of the min heap exceeds that k value, we have to remove the smallest sum using that heap q.heap pop, right? Because we don't care about that smallest sum as we already have k larger values, right? And this ensures that the heap at any iteration only stores the k largest level sums when it actually exceeds, or the length of it, or the number of level sums in that min heap actually exceed the k value. And ultimately, outside of this while loop, we simply have to return min heap at 0. But again, we can only do this if the length of the minimum heap, if the length of the minimum heap actually equals k. If it doesn't equal k, we have hit our bad base case again, and we have to return -1. Right? So again, if the minimum heap contains only exactly k level sums, we can effectively return the smallest sum in the heap, which would correspond to that kth largest sum. But if there are fewer than k levels in the tree, of course we have to return -1. So as you can see, if I were to submit this right now, unless I made any syntax errors here, they should be accepted. Okay, see what I did wrong here. Heap pop. Oh, oops. Sorry about that. I literally forgot to pass in the minimum heap data structure while popping. But as you can see, this is just about as efficient as you can get. So to better explain what the code actually does overall, We first have to traverse the binary tree level by level using that BFS algorithm. Right? And we have to sum the node values at each level and keep track of that k largest level sums using that minimum heap. And at the end, we have to return the kth largest level sum, or just -1 if there aren't actually enough levels, right? So for the time complexity of this program, this is going to be big O of n because we traverse all n nodes in the tree once, and big O of log k because each heap operation for inserting and popping is defined to take big O of log k time, and so the overall time complexity of this code is going to be big O of n log k. And for the space complexity, this is going to be big O of k for the size of the minimum heap because that's at most k, and big O of n for the queue because it can hold up to n nodes in the worst case, okay? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.